So I'm going to be a little bit more formal in this lecture than in the last one. Remember in the last lecture I said we were going to try to, in some sense, formalize or axiomatize an essentially mythological situation. That is to say, we're now going to try to do a formal definition of a d-dimensional quantum field theory. So the mythological situation, which is meant to be in the background, is that when we have a d-dimensional manifold, which we think of as a space-time, then we have some notional space in our minds of fields locally defined on M. So scalar fields or spinor fields or connections, all sorts of things they might be. And we have some action functional, which is also local in the sense I talked about. And associated to this, notionally, we want to define some kind of measure, which formally, I said, we write like that, where that's Planck's constant. And from this point on, I'm mostly going to make Planck's constant equal to 1, but I'll put it in there for last time. This is meant to be a measure on phi m. And we want to, with respect to this integral, perform certain kinds of, with respect to this measure, we want to perform certain kinds of integrals. So the kind of thing we want to perform is when we have a point x in M, let's write phi m x for the jets of fields, whatever they are. So that means the integral jets. So things that depend on the values of the fields and their derivatives up to any order at the point. Obviously there's a map then at the any field is meant to have a jet. And we want to be able to evaluate, well, we're going to define for any x, we're going to look at the C infinity functions on this. And what we're interested in is notionally some multilinear maps where these are distinct points of M, which notionally are like this. Something which I'll write usually like this. Sometimes there's an M on it, which in principle is meant to be the integral over the space of fields of so these are the things which are actually, this is meant to be encoding the field theory. So let's mark that equation. That's what we actually are going to be talking about, and this is mythological background to it. But we'd like to talk about what properties these functions should have that are motivated by this mythology. So my angle on this is to give the following formal definition. So we can in some sense forget all that for the time being. And we'll say, I'll give the definition, and the definition will need lots of comments, which I'll make after I've given it. So this is two-dimensional. And so for each compact-oriented Riemannian minus 1 manifold, n, and give a topological vector space like Hn. So it's not necessarily a Hilbert space, but I'll write it Hn. And for each cobordism of compactable electric domain, and I'll write it sometimes like this, just to indicate that M is meant to be some kind of cobordism between a manifold M0 and a manifold M1. So that picture we give a continuous trace, well, a trace class, what's that? Continuous trace class linear map UN. So that's the end of the data, and we want 3 properties to hold. Following. First of all, concatenation. So all of these will require commentary. Which is just that if you string together 2 cobordisms, M and M prime, then we get and the property we want is that if we put the 2 together into a single cobordism, then that is composite. So the second property I'll just call tensor, which says that the kind of tensor functor, that the space associated to the disjoint union of 2 manifolds is in some way canonically the tensor product. And similarly, cobordisms, if you had a cobordism of this and a cobordism of this, then the cobordisms were tensor. So, and thirdly, smoothness. Which I won't back down anything. That's just meant to say that if you have a smooth family of manifolds parameterized by some smooth parameter space, then all of this data varies smoothly. So the spaces would, the vector spaces would form vector bundles over the parameter space and so on. I won't say any more about that at the moment. Well, so that's a kind of definition. And I gave it as a kind of joke, I think in 1986, in a meeting that Herzog organized at Schloss Ringberg in Bavaria. And for a long time, I thought it was more of a joke really than other people did. But it sort of caught on, and I was slightly slower than other people, I think, to think it's worth taking it seriously. But I've somehow feel I'm identified with it now, and I'd like to defend it.
The second one behind it.
Right?
Yeah, the second one.
Oh, okay, well, yeah, well, okay, well, I might as well, yeah, so we need some, I wrote down various comments, but I have not So some of these things I'm going to tell you about right away, and some of them not. Let's put various comments. Well, one of the most important, and that's going to be the main actual topic of today's lecture, is this M that is in the definition, that's meant to be a space-time. Now, space-time in ordinary physics comes with a Lorentzian metric. Space and time are different. And I've given you an axiom system with Riemannian manifolds. So the first point is Lorentzian manifolds versus Riemannian. So we're going to be talking about that presently. The second one is I assumed everything was compact. I talked about compact manifolds with boundaries, and so on. So the compactness assumptions. I'm not going to be talking about them very much today, at least. I hope I'll come back to them a bit later. But just in a word, roughly speaking, when one makes these assumptions, what one is saying is that one is only going to be talking about what physicists would call the ultraviolet behavior and not the infrared behavior. We're going to be talking about what happens at high energies and short distances rather than the opposite. But I'll say more about that, I hope, in a later lecture. The next thing is more kind of mathematical, technical point. What kind of topological vector spaces? What kind of topological vector spaces do we allow? What kind of tensor product? And perhaps I should say something about trace-class operators for those who don't know about such things. So there's a sort of functional analysis side. Part of my message is that this, although it seems something you should be careful about, in fact, it turns out to be very easy to deal with this point because of the nature of the formalism. So the next thing, in fact, I really can't remember what things were I can look. I'm using improved technology. I bought bifocals so I can actually see my notes, which I couldn't do in the last lecture. I have very bad eyes. So now the next point is that this, one of the many ways in which this definition is a bit dishonest. You see, it didn't really actually make sense. If you were looking carefully, you will see that you can't concatenate two cobordisms, because this is meant to be a smooth manifold with boundary, and this is meant to be a smooth manifold with boundary. The two boundaries are identified, but when you stick them together, you don't have a smooth structure unless you choose one. So the way around this is to say that this thing that we call HN is actually associated to a germ of a D-1 manifold inside a D manifold. In other words, one should think of N not quite in the way that I drew it, but as a little neighborhood of a codimensional thing inside a D-dimensional manifold. And a germ means a class of neighborhoods of something N, where you identify two neighborhoods if they have a common, you identify one neighborhood with another if it's N. So obviously if you have an actual neighborhood, then you can concatenate. Well, that again will be important later. The next thing is I ought to say something about unitarity, but I'm going to postpone that. Because usually we I'll come back to that later. And finally, I should mention that there are a lot of possible different structures. So we might consider other classes of manifolds. So I've taken oriented Riemannian manifolds. We might, for instance, want them only to have a conformal structure, or we might want them to have a Riemannian structure together with some additional structure like an auxiliary vector bundle, or possibly with a connection or something like that. Or we might want them to have even less structure, the extreme case being where we just have smooth manifolds and no further structure at all except the orientation. And then people usually talk about a topological field theory, not a terribly logical use of words, but that's become traditional. So that's the minimal kind of structure. Well, so that's the setup. So all of these are things that we're going to come back to. Now, there are a couple of lemmas that one immediately proves from this, which I'm not going to dwell on now. For example, we can consider the space associated to the empty manifold. This is the empty n-1 dimensional manifold. Clearly that is canonically the complex numbers, because obviously if you take any manifold and take its disjoint union like that, you have that. So Hn, Hn to all n, and that clearly implies that. One of the other things one traditionally reads of is that if we reverse the orientation of n, so let me put a bar, that means n with reversed orientation, then it's meant to follow from this axiom system that this is canonically the dual vector space to this. Now, you see, in order to say that more precisely, I have to say several other things about the nature of the topological vector spaces and so on. So this is something which, just bear in mind for the time being, we'll come back to it later. Finally, one of the other traditional things that we usually read off is that when you have a cobordism from something to itself, so that we have the same n at both ends, then we have un and then it should follow from these axioms, that the trace of this is just m hat. M hat, that's the thing you get from this by making its mapping torus. You identify the two ends by the given identification, and you get something that more or less sticks over a circle. That's the mapping torus, let's say. And what does this mean? Well, you see, this is a map that's a manifold without boundary, so this would be a map from the complex numbers to the complex numbers. And think of maps from the complex numbers to complex numbers as complex numbers, trace. And I said these were trace class operators, so it's meant to have a trace.
Is Hn locally complex?
Yes, but I'm going to absolutely, yes. But so I'm going to come back to the topological vector space aspect, but not quite just at the moment. Well, so one of the things so you might think that this is in some way rather little information. So you might think it's too little, and that it doesn't look in the least like what we thought a field theory ought to be. So how do we get the maps which I call star up there? You see, supposing we have an M, and we put some points. Then how do we get some data, such as what I want? Well, first of all, I have to tell you what the spaces OX are. Well, essentially, OX is just going to be the space H associated with the boundary of U, where U is some little neighborhood, open neighborhood of the point. So it's a little disk-like thing like that. Imagine it's very, very small. And then take its neighborhood and take the space associated to that. But of course, these things form an inverse system. And strictly speaking, I am going to take the inverse limit, where X sits in the interior of U. So these things are ordered by inclusion. And you see, when you have one neighborhood contained inside another, then the difference between the two is cobordism from the outside one to the inside one, so it will give you a map giving us an inverse system. But don't worry too much about that, just think of it as being the space associated with the boundary of a little tiny neighborhood. Well, then you see, we want to get in this situation like this. But you see, if we define a manifold by taking out from M the disjoint union of all those little disks, or strictly speaking, their interiors, so that's the manifold puncture, you can think of that as being a cobordism from the boundary of the disks to the empty manifold. I'm assuming M is a closed manifold. And you see, the space associated with this is the tensor product then of the spaces which I just said, well, O is I, and so U hat will go to H, the empty set C. So we do output these things. And furthermore, the obvious thing we have incorporated is the thing which I told you in the first lecture was the main thing we want to incorporate. That you see, if now we divide this manifold M into two by a membrane N, so that M is now and supposing x1 to xt in here, xt plus 1 to xt plus 2 to p plus 2 is k in there, then you see we know that we can write this cobordism as the composite of two cobordisms where this is M1 minus the union M1 the other side. And you see, this will be a cobordism from the boundary of these things, N, and M2 will then be the cobordism so we would have written our number, the number we're interested in, as precisely the pairing between a space, an element which we could call A1 to AP, which will be in that. It's pairing with something in the dual space, which we can write in that. So we're precisely ensured that the way these numbers factorize is through, so to speak, a vector space associated with the interface. That's the one essential point. Of course, that's not saying very much. I mean, that's still a very weak statement, and we need to say a lot more. Well, in this lecture, I mainly want to talk about this question of so-called weak rotation, the relation between Riemannian and Lorentzian manifolds. But I'll just say one thing, other thing before coming to that, namely, let's just consider the one-dimensional case. So the case P equals 1. Then, you see, we only have one interesting germ of a naught-dimensional manifold. So we have some space. Well, we should really have two spaces. We can orient it that way or that way, which is somehow in duality. So we have really two dual spaces. What will be O of the point? Well, that's what I should have said is, we have, what do we have in the way of one-dimensional manifolds? We think of the one dimension as time. The only property the Riemannian manifold has is its length. So we have a one-parameter semigroup. I'll just mainly write this as H. So this is a contraction semigroup of trace class operators. And that's really essentially all we have. So because it's a trace class semigroup, it's determined by a sequence. I'm going to sort of sneak in the unitarity, which I'm going to come back to later, because I just want to say this rather vaguely at the moment. Let's assume that this contraction semigroup consists of self-adjoint operators. We'll be talking more about that later. Then the complete data is just given by the sequence of eigenvalues, the sequence of numbers, real numbers tending to 0, and that's the complete information. In other words, we have an operator in Hilbert space with a discrete spectrum. And what are the observables associated with a point? Well, you see, they will be, we'll be looking at H dual tensor H, in some sense yet to be described as tensor product, associated to each little tiny interval around the point that we're studying. And we'll be taking the inverse limit of these, where we map things in both directions by this semigroup. So what we will actually be, when we take that inverse limit, what we will actually be looking at is things which we can think of as very highly unbounded operators, which will become whatever kind of good kind of operators, whatever this tensor product is going to be, when we compose them. So we'll be looking at operators in some very unbounded, generalized sense, with the property that they will become, when we compose them like that with these strongly contracting operators, these will become rather good kind of operators. So they'll be very unbounded kind of operators, very much the kind of things you can't compose. So this will be very far from being an algebra, but it will have the structure of it.
But you have then probably domain questions.
Sorry? Yeah, so the domain of this operator will be the image of a typical element of this contraction semigroup. So the example to have in mind is when we take H to be the L2 functions on some compact manifold M. So this M is not, let me write it as P. This is some auxiliary from nothing to do with the space-time. The space-time is one-dimensional in this. Imagine this is this, and imagine the semigroup is the usual e to the minus, where this is the Laplace operator, P. So this is the heat semigroup. T is time, is interval. This is the case where the system we're studying is a free particle moving in the Riemannian manifold P. This is the typical Hilbert space of states. So we're looking at the heat flow. So the information is completely contained in the spectrum of the so the classical system, of course, the classical phase space would be the cotangent bundle of P, and this is a quantization in terms of that language. The information we have gathered here is no more or less than simply the spectrum then of the Hamiltonian. And I'm sure you're all familiar with the famous discussion of Mark Katz about hearing the shape of a drum. It's a famous problem, of course, how much you can determine about a Riemannian manifold when you know the spectrum of the Laplace operator. You can certainly determine the dimension of the manifold, you can determine its volume, you can determine lots of things, but you don't determine it completely. So you think of this one-dimensional example of a quantum field theory as like, so this was the point of view I was trying to push in my first lecture, as something analogous to a non-commutative space. And if you had just a one-dimensional, this is just a quantum system, it's something like a non-commutative manifold. Now, one of the themes of this lecture, apart from quantum field theory itself, is things motivated by string theory, when we discuss two-dimensional quantum field theories and try to say that while a one-dimensional theory is a very crude approximation to a manifold, a two-dimensional theory is has considerably more claim to be considered as some kind of generalized manifold. I'll say one more thing there. Those of you who study sort of traditional non-commutative geometry will know that his concept of a non-commutative space is often expressed as a so-called spectral triple, which is not only do we have this information, but we have a mod 2 grading and a little bit more, so that what we are recording is really not just the Laplace operator, but the Dirac operator. A little bit later on, I'll talk about that, and that corresponds to what's called a supersymmetric one-dimensional theory. And it's supersymmetric two-dimensional theories that really we should think of as the things entitled to be called generalized manifolds, generalized Riemannian manifolds. But that's not for the moment. Now I want to change ground and talk about the relation between Minkowskian and Riemannian manifolds. And that I'm fairly sure I'll have time to do So this question is concerned with how one encodes the positivity of energy in physics, in quantum theory. If you think of the most elementary treatments of basic quantum theory, so this is not part of my picture, but just part of traditional quantum theory, we traditionally have a Hilbert space of states, and the time evolution is given by, I'm going to suppress Planck's constant from now on, is given by some operator like this. This is evolution of states, the time t, where this is some self-adjoint operator, the Hamiltonian. Now, one of the basic things that any properties any system ought to have is that energy is positive. This Hamiltonian is meant to be the observable of the system. It's a self-adjoint operator on H. It's meant to be a so-called observable. It's meant to correspond to the energy of the system. And that ought to be positive. So we want H to be a positive self-adjoint operator. That's meant to be equivalent to saying energy is positive. Now, a good way to encode that statement, this is meant to be a unitary operator, of course, because of time evolution. So a good way of encoding this is to say that the function t to e to the iht, which is a unitary semigroup, as written. This is the boundary value of a semigroup defined for t in the upper half plane. You see, because if we give t a positive imaginary part, this will be e to minus something positive, and that will then be a contraction operator. So it's a semigroup depending holomorphically. So I'll just write a holomorphic semigroup. In other words, this should be a holomorphic function of t, and it should be of contraction operators. Make things smaller.
You assume that also the Hilbert states are separable.
Sorry?
Separable. The Hilbert states should be.
I certainly had that in mind, yes. But again, for the moment, I'm just sort of, yeah. I mean, this is just meant to be the traditional picture of quantum mechanics and the positivity of energy. So clearly, when you have such a semigroup, then being able to extend it like this is saying that H is something positive. Well, now, that's a very non-relativistic way of looking at it. And in special relativity, of course, one would say that one had, if we call this operator ut, we would say that we had some operator u psi, the unitary operator, depending on psi in Minkowski space. R1, 3. So this is meant to be standard Minkowski space. And in special relativity, we often consider a system where we have this unitary operator corresponding to being able to displace the system any way we like in Minkowski space. And the relativistic generalization of this is to say that this is the boundary value of a contraction, of a holomorphic contraction semigroup defined for psi in a kind of generalization of the upper half plane. Plus IC, that will be contained in C4, where C is the positive light cone. yes, definitely. I mean, at the moment, I'm going to just motivate something I'm going to put in to my discussion. At the moment, I'm just sort of saying, in traditional quantum mechanics, we have a Hilbert space of states. We have some Hamiltonian operator. Usually, that will be some unbounded self-adjoint operator generating a unitary semigroup. And the special relativistic generalization will be like this, where C is the positive light cone. So in Minkowski space, we have time and space, and we have the light cone, the vectors which, in a suitable frame of reference, go forward in time. And the interior of this is meant to be C, the positive light cone. And if the imaginary part of this vector, so this is a complex and open set in C4, and if psi is in that, we have some contraction operator and then called the semigroup. Well, so that's the positivity of energy in old sort of beginning quantum mechanics. Now we want to generalize that to the framework that I'm working in. So we now want to say how do we expect to do that. Now in traditional treatments of quantum field theory, you see, because what you did here was you started with Minkowski space and you looked at this domain inside its complexification. Traditionally, people often think of those functions that we had, which were meant to contain all the information, those things we had right at the beginning. And we think of moving these things out of the original space-time manifold into some complexification. In other words, we try to let the points x, which start off in M, go into some domain in some complexification of them. Well, that's not a very good point of view, as far as I'm concerned, in that normally a smooth manifold doesn't have any complexification. Maybe that's not so serious. You can consider ones which at least look, to some extent, could sit inside a complexification. But it's certainly better, if you're thinking of the path integral picture, not to think in terms of that, but to think of it in terms of a different way. Remember our mythological picture where we have a space of fields and functions. And we should think of this as being a Riemannian manifold, so it's equipped with a Riemannian metric G. And we should think of the action of a field as something which we calculate using the Riemannian structure. So instead of changing the points of M, we want to keep the manifold M fixed. And what we want to change is its Riemannian structure. So what we want to do is we want to define a domain of complex metrics. On M. M is just as before. So I'll call it with certain properties. You see, in other words, when we were in that situation which was associated to a time displacement of t, the thing that we want to change is not, we don't want to move this point off the line into the complex plane, but we want to change the metric so that t is allowed, t is the length, and we want to make that be a complex number. So a complex metric, G, will be a cross-section of the symmetric square of the cotangent space at each point, but we'll complexify it. So if you chose them in local coordinates, it's given by a symmetric d by d matrix with complex entries instead of real entries. And this domain is going to be defined locally. So we're going to pick a domain. So this good domain is going to be, is just sections of some local metrics. In other words, we're just going to put a local condition on this symmetric matrix. So let me tell you, so now what is the idea going to be? The idea is going to be that given M, we're going to have this huge infinite dimensional space of metrics. Now, it's going to be a complex manifold. It's going to be an open subset of this whole space of the all complex metrics. So it's going to be a complex domain. It's going to have the real Riemannian metrics as a real slice, and it's going to have the Lorentzian metrics sitting on the boundary. So in what's going to be called the Shirov boundary. In other words, by complexifying, I've doubled the dimension, the real dimension of the space of metrics. We're going to have these boundary things here. Well, let's explain it point by point, first of all. I mean, you might think, you see, remember, in some sense, we're trying to look at some path interval over all fields, which remember was this is an oscillatory interval. It would have a better chance of existing if instead of being oscillatory, it was something more like Gaussian. So we know if we have an integral just in finite dimensions, half x transpose ax dx, well that's a matrix. Well, that's a symmetric real matrix. Then we know we can make, this is conditionally convergent integral in finite dimensions. If we make the imaginary part of that positive definite, going to the so-called Ziegler domain, this will become like an ordinary Gaussian integral and it will really exist. So the first thing you might expect us to do is to say, well, let's just simply take the metrics such that the imaginary part, I'll work from the real to the complex, such that the real part of the metric was positive definite. That's on the right track, but it's not quite right. So let me tell you what the real condition is. You see, let's think of an example. If you think of a standard scalar field, then you know the actions of a scalar field on a manifold is given in some traditional notation by something like this. I'll write it in very old-fashioned notation. And maybe with a mass term if you want. And then we have to put, however, the determinant of G to the minus half dx1 dxd. It's very important that you put this in. So the thing that we want to be positive is not the metric itself, but the metric with this thing in it. So we want the thing that we'd like to be a matrix. Sorry, if I'm doing it that way, it should be G is the so this is G inverse. The real part of that we'd like to be positive. So for instance, in dimension 2, that only depends on the conformal structure, because if you multiply G by a scalar, the two factors would cancel. So that would be only conditional on the conformal structure in 2 dimensions. Well, it turns out that the right way to think is in terms of the Hodge star operator. which the metric defines. At each point, if we have a metric given complex, we will get something that takes p forms, the d minus p forms. These all complexified. And this is the thing that we want to put a condition on. Because we want to be able to say not just that this metric will be good for scalar fields, but it will be good for the essential term in all kinds of field theory we might be wanting to think about. For instance, we might want to be doing Yang-Mills gauge theory, where here phi will be replaced by a connection form, and we have some other example. And the thing we want is that this star has the property such that alpha star alpha, we take alpha as an element of this. So that's in the top exterior R, which is one-dimensional. We want that to have positive. Also see that on the boundary of the domain, you have things which have only one negative dimension. You see, if you make just one of the lambdas be minus 1, then its argument is pi, and you've got to the boundary already. So you suddenly can't get two things having a real negative lambda. So this is a very nice domain, and it has on its boundary, it's called the Shilov boundary, these Lorentzian metrics. Now, well, there's a long history to this, in that in 2 dimensions this had already been much studied, in fact independently by both me and Conservatives in 1986, when I think he was in primary school, and we really didn't interact with each other at all. Well, we, sorry, I got very late in this section. I'm afraid I'm going to have to put a little bit of this into the next lecture because it is rather important for the sequel. So let's consider the case D. So let's consider the case D equals 2. So supposing we have a so we're looking at surfaces. If we have a 2-dimensional tangent space with a complex valued quadratic form on it, non-degenerate, that's determined by giving its 2 null directions. So up to a scalar, the form is determined by, if you look at the projective space made from the tangent space, the complexified tangent space, there'll be 2 null directions in it, 2 complex directions in which the quadratic form vanishes. Now this condition is exactly equivalent to saying one of these 2 directions is in each half plane. So this is the real projective line, which is the projective space of the real tangent space, and this is the complex projective line coming from the complex tangent space. And this condition says that these 2 points are in opposite half planes. On the boundary, so the real ones, the ones that are real valued quadratic forms, are where these 2 points are complex conjugate, with respect to the obvious complex conjugation. And the boundary, the Minkowskian ones, are when these 2 points both come to the boundary, and then you'll have 2 real null directions. So they will be the 2 like directions which you have on a surface with a Minkowskian metric. Through each point we have 2 like directions going. Except that there's a degenerate case where these 2 points come together. That will be when the 2 like directions coincide. Now, I think I'll just, I'm going to have to come back to this next time anyway, but I want to explain, I think it would be better if I stop at this point, and I'm going you to the time when everyone has to be shot, and I'll start this again at the next lecture. I'm sorry I got behind my issue, but I'll stop now.